Audio, image and video files can be very large. The amount of data captured in high-resolution video is staggering. In order to help with this, many file formats include compression in the encoding process. The amount of compression that is possible will depend on the nature of the data. Compression is made possible by removing redundant data. Some data has very little redundancy, like this brick, and so is not very compressible. Other data, like this sponge, is full of redundant data and can be compressed a lot. Some compression techniques work at bit level, meaning they simply look at the patterns of ones and zeros and try to optimize based on repetitions. These techniques take no account of what the data is used for and can be applied to any type of data. An example of this is called run length encoding, or RLE. Here is a block of data. It contains 256 bytes of ASCII data. Each letter consumes 8 bits, or 1 byte. With RLE, we encode by scanning through the data and storing value pairs. The second value is a data value, in this case W or B, and the first value is the count of that data value. So looking at the start of the data, we have 66 W's, followed by 12 B's, followed by 4 W's, and so on. If we follow the process through, we end up with this. This contains 67 characters, meaning 67 bytes of data. So we have a compression ratio of 256 down to 67, which is around 4:1. This means we can save on storage space, using just 67 bytes. We can apply the algorithm in reverse to reconstruct the original 256 bytes. No data is lost through these conversions, so this is called lossless compression. The amount of compression possible depends on the actual data. Imagine our data is a stream of alternating W's and B's. WB, 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 and so on. In this case, we have no long strings of W's or B's, and the encoded result will actually be bigger than the original. Run length encoding is used mostly for storing pictures. BMP files, developed by Microsoft, can optionally use a form of RLE for compression. For applications to use files, they need a little more information than just the raw data. Let's take our earlier example. This data is pretty meaningless. However, with a little more information about the file, we can make some more sense of it. Let's add 2 more pieces of information. This is an image file in which W means white and B means black. The size of the image is 16 by 16 pixels. Now we can render this file as an image. First, we unpack the RLE to get to the original data and apply the 16 by 16 sizing. Then we render the image. This is of course magnified. 16 pixels is very small, and icons would typically be about 10 times bigger than this. The extra information which describes the raw data is called metadata. It is normally stored at the top of the file and is called a header. The precise format of the header and raw data is defined by the type of file. So for a BMP file, applications know exactly how to interpret the file contents. The BMP format includes a few more details not covered here. However, using a hex editor application, we can inspect the contents of our BMP file. This is the contents of the screen icon file, with RLE compression enabled and 8-bit color depth. The first 2 bytes, 42 and 4D in hex, are ASCII encoded and correspond to BM, standing for bitmap. All the data from the start to the highlighted section is header information. The highlighted section contains the actual data. Another way to reduce redundant data is to look for repetitive patterns and assign these a dictionary value. In the compressed data, you only store each repetitive pattern once, and when it occurs in the data, substitute in the dictionary value. The dictionary values can be much smaller than the original data. Here is a simplified example to illustrate the point. Let's assume our data is a text string. The cat sat on the mat. This consists of 22 bytes of data, assuming we are using ASCII encoding, 1 byte per character. We can see there are some repetitive patterns, so let's assign these dictionary values as follows. THE space equals 1, a T space equals 2. Now, rewriting the phrase, we get 1C2 S2 ON space 1 MAT. This only consumes 12 bytes, almost 50% reduction. This is an oversimplified example, but is the basis for how zip files work. It works especially well with text files, but is actually a bit-level compression algorithm, so can be applied to any type of file. Technology. Made simple.